We are in the middle of Storm Eunice and you can hear the rain beating down on the roof, and it's causing havoc. They're bringing trees down on the road so people can't get around, the power lines are down, telephone lines are out. It really makes you think about how you can generate your own electricity at home. Unfortunately, there are just a limited number of options. I mean, you could buy yourself a generator, a diesel or petrol generator, because you can't drive to the petrol station. It's as much use as a chocolate teapot to you. You could set up your own wind, you can have some solar. If you live by the sea, we've got wave power, but that's pretty much it. And of course, with all this rain coming down, it makes you think, well, if only we could extract the power from the rain, because rain carries a charge. As it comes down as a water droplet, there is a charge on it, and if that charge could be collected, wouldn't it be awesome? Now, there are efforts to collect rainwater and use that to drive a generator of some kind. Quickbills did it. He used his roof and his gutters and he put it down the downspout and forced it over a Pelton wheel and generated from that. But there are other methods of generating from rain. Now, they've been a bit embarrassingly low in terms of their ability to generate an amount of electricity, because they rely on something called triboelectricity. Triboelectricity is that electricity you get by rubbing two surfaces together. Some materials have a propensity for giving up electrons, some materials have a propensity for taking those electrons on board. So they will get a plus and a minus charge as you rub them together. The famous one is a glass and cat's fur. If you get a piece of glass and you get a cat's fur and rub it, you will create a charge, a static electric charge, that's responsible for those shocks that you get sometimes when you touch a metal cupboard or a metal bed when you've been walking on some nylon carpets. It's the thing that if you rub a balloon on your jumper, you can stick it to a wall or you can make your hair stand up on end. That's triboelectricity, and it's present in just about everything. Now, in order for that charge to stay, then it needs to be an insulator. A bit of metal, the charge goes away almost immediately and you can't notice it, but it still happens. It's just the charge grounds very quickly. And triboelectricity is the basis of an awful lot of nanogeneration schemes and energy scavenging schemes, including rainwater. Now, it's been the case that, as I say, that amount of energy that could be collected has been embarrassingly small until recently. There's been some work that's come out of the University of Hong Kong. What they've done is essentially make a whole gang of little capacitors, and when the rainwater hits that capacitor, it generates a huge amount, a surprising amount, and they reckon it's about 50 watts per square meter. When you think a solar panel produces 150 watts a square meter, that's pretty awesome. I mean, solar panels will be rated at something like a kilowatt per square meter, but that's the rating, it's not what they produce. They actually produce around about 150 watts. And of course, if you live in a rainy country like England or Oregon or South Island, New Zealand, you get far more rain than you do sunshine, so your solar panels are producing very little. If we could create a rain panel that's producing 50 watts per square meter, we have a real alternative. Now, the way these things are made up is there is a layer of conductor, and what's used is indium tin oxide, and on top of that a layer of insulator, which is polytetrafluoroethylene. Polytetrafluoroethylene is this stuff. It's plumber's tape. It's the same stuff that you find on your frying pan. This is PTFE tape, and it's used for plumbing, both water and gas. So that material is on top of a conductor, and then there's a tiny collector. When the rainwater hits it, it forms a capacitor where the rainwater with its charge is one side of the capacitor and the ITO is the other side. When the rainwater opens up and touches the electrode on the PTFE side, a current flows. Now, it's not an embarrassing amount of current, it's a huge amount of current, and in the demonstration, 4 of these little things can actually light, I think it's up to 200 LEDs, and you can see the LEDs flashing off and on as the water drips over them, which is just astonishing. Now, of course, with something like that, aren't you just tempted to see if you can do a replication? I mean, in my mind, what you would do is get a piece of aluminium, put some PTFE on it, put a little electrode on the PTFE and take it out into the rain. We can make a homemade version astonishingly easily. Kitchen foil, plumber's tape. All we've got to do is stick some kitchen foil onto a plastic background and then some plumber's tape on top of it. So that's exactly what we're going to do. So there's my bit of plastic with some kitchen foil stuck on with double-sided tape. I've got a bit of insulation tape here, it's gaffer tape, and that's so we can hold it without actually making electrical contact. That's a bit of plumber's tape, which is PTFE, and again some double-sided tape stuck on it. Some aluminium tape. This stuff is from heating and ventilation. It's used as a seal. And that's it. So I've put it in the stand, which is why we put that insulator on, and here it is just above this paper towel to catch any water drops, because I'm going to drop water on it. This is just ordinary tap water, which is what they used in the university. They did tap water, rainwater and seawater, and they found that tap water and rainwater worked better than seawater, because remember, this is about the charge that's actually in the raindrop as it falls. So it's got nothing to do with the salts in the seawater, it's got nothing to do with the movement of the rainwater, it's got to do with the charge in the rainwater and how that charge is transferred on this. This is basically a capacitor. So we're going to drip some tap water on it. I've got the usual setup here with my phone on the meter, and let's have a look at the meter when the water droplet rolls over the capacitive contacts, because that's what you're interested in, how it rolls over it. Look at that. When we get it rolling over, we get this huge amount of energy. I mean, 100 millivolts may not seem like a huge amount to you, but remember, this is just a couple of strips of Ali on some PTFE. I think it's awesome, I really do. Now, that is just with the charge. Have a look at this. This is 4 of them lighting 200 LEDs. So here's a close-up, and this is when the water rolls over the contacts. Watch what happens to the voltage. See that? Okay, so it's a method that works. It works really well. But what excites me about it, what interests me about it is, remember, it's made from kitchen foil and plumber's tape. So this is something you could actually make yourself. When people make their own homemade solar cells, they're always a bit weedy because they use copper oxide, and if you want to get a decent solar cell, well, you've got to buy one. But it seems that this is something we could make. Something we can make from normal store ingredients that has 50 watts per square meter, and that is just awesome because you could actually go out and do this. Now I understand that I'm really just demonstrating how to make a single cell and how simple that cell is, but to reproduce this on a larger scale it would be lots and lots of small cells. That's all you're actually wanting to do. You're not wanting to build a massive cell, lots of little small ones. Put them on a panel, and the panel can clearly be anything, any lump of plastic or wood or glass or whatever, obviously non-conductive, and you're going to have yourself a electrostatic triboelectric rainwater generator. Remember, it's got nothing to do with the movement of the water or the salt content, it's the electrical charge the water already has in it that you're collecting. It's the same thing that makes lightning. You're basically collecting lightning, which I think is just amazing. Now there are lots of things as well for experimenters, so if you wanted to make this you could just go out and make it. But there's obviously a lot of experimentation that could be done with this. There are questions that need answering. So is it the movement that's interesting? Is that what's generating? In which case, can we just dip this in a stream? Could we put it in a wheel arrangement? Could we flow water past it? So many questions that need answering with an arrangement like this, and the arrangement, stupidly simple to make. Kitchen fork, plumber's tape, pair of scissors, and a bit of patience, and you're off. Now all I've done here, which is version 2, same bit of plastic, same bit of aluminium, but now it's painted with our conductive ink. Carex painted it with his own conductive ink. If you want to make a conductive ink, then I've done a really good video on how to go about doing that, and it's video number 1381. If you want to find these videos instantly, just go to the channel and type in the number on the search bar, it'll just pop straight up. So if you want to make your own ink, follow video 1381. If you want to buy any other ink, go out and buy another ink. But it works beautifully with a conductive ink. So, took my bit of plastic, put my bit of aluminium on it, painted it with our ink. Now then I began to worry a little bit. This is going to go in the rain, and I was wondering if the rainwater would actually eventually just wash the ink away, or as I've been mentioned, corrode the aluminium. So what I did then is really simple. There's some outdoor varnish. It's a polyurethane varnish, leaves a polyurethane coat. All I did with this was dip it in, let it drip dry. When it was dry, of course, it's got a fine polyurethane coat over the top of the conductive varnish, conductive ink. So if you make your own conductive ink, you can make it water-based, just dip it in that, and you'll have a waterproof surface. Now, of course, polyurethane is an insulator, and as we know, this is basically a capacitor. So it now has a layer of insulation on it. So it no longer needs the PTFE. So the PTFE is gone. So remember, this is the original with its strip of plumber tape there. This hasn't. This is a layer of aluminium, layer of our ink, dipped in the varnish, and then the electrode stuck straight on the top. What I'm going to do now, obviously, is try it. So I've got a little bowl underneath here, clamp holding in place, and I've got a dropper funnel right there, so I can turn it on and get a drop of water on it. And of course we've got our meter connected, so we're going to connect our meter, drop some water on it, and see what happens. There we go, 2 simple but huge improvements. 1, paint your aluminium with some conductive ink. 2, dip it in some polyurethane varnish, then you can get rid of your PTFE and you get a huge improvement on the output. Okay, it works as a rain generator, but what about if you made it into a wheel and it would dip in and out of the water? Now I tried leaving it in the water and it doesn't work. It must move through the water or the water must move over it. I mean, it's frames of reference, so it doesn't really matter which one moves. The water has to be moving over the surface. So people said, what about a wheel? So I thought it was brilliant. So of course, what I'm holding here is a wheel. Now, it's nothing more than 8 of our little rain-worn generators. So I've made exactly the same way. There is a generator. It's a piece of plastic covered in alley, painted with our ink, and then varnished. And then obviously I've stuck it to a wheel. Now, in order to get this to work, I need to connect them. And to connect them means taking some kind of connection from the edge of the aluminium here and feeding it out so that it doesn't actually interfere. And I'm using a bit of wire. Now, it's dead simple. Just take a bit of wire and nip off quite a large end of it. This is quite a fine stranded wire, so it makes a brush actually. And if you feed that brush through the hole, and then press it against here and tape it down, you have a great connection. The resistance of this connection is about 0.002 of an ohm, so it's a good connection, and it is literally just a push connection with a bit of tape on it. So we feed the wire through the hole that I've made, and then we can make a nice connection on the other side when we've assembled everything. At some distance, press it there, a couple of bits of tape, hey presto. So let's finish off those. And there it is finished. So we've, remember, taped it to the back here, fed it through this disc, spot of glue, and then we've got our contact points that we can join together. And of course I put the other disc on. Now what we need to do is to put the connection on here, the electrode on here rather. And so for that we need a thin strip of aluminium that we run there, along there, and then onto here, which is where that connection point is, and we're going to use ducting aluminium to do that. So there it is with its electrodes attached, running up here and running to there. So now we'll give it a quick test and make sure that one of these works. So I've just connected up this one alone, and we'll pop that on there and dip it in and out and see if we get a result. Oh, look at that! Okay, 0.6 of a volt. That's awesome. So the next job obviously is to get this into a wheel that will rotate. So though the axle, all I've done is take some 8mm copper pipe and glue them onto a bit of wood, because there'll be slip rings. So we have an insulator here, and then we have the conductor there. I connect all those wires to the slip rings, and then obviously lay a brush on each of those, and that's how we're going to collect from it. Okay, so we've got it set up. Now obviously I haven't done this in a particularly refined way because we're testing the wheel. Luke's just going to push the insulated end, and of course that's going to bring the wheel through this still water. This still water is just tap water. Obviously I've got the pip set up, and we're going to be reading the voltage. Now this is connected in parallel. And it's connected in parallel because each wheel dips in by itself, and we're going to get the voltage will be the same across the whole wheel, and the amps will be the same across the whole wheel. Et voila. So we're going to record a pip, we're going to give it a bit of a spin, see what we get. And I'm the brushes. Okay, mate.
Ready to rock?
Ready to rock. A little bit faster. Try and get it on there. There you go. A little bit slower. Okay. Okay, thank you, mate. Okay, so we got about 0.4, 0.5 of a volt. You can see that there's still a voltage on it, and that's because it's a capacitor. So it won't do anything until we discharge it, or it'll discharge itself slowly. But there we go. It actually works as a wheel. So, as a proof of concept, putting it in a wheel arrangement works a treat, actually. Now, we did get this up to 0.6. Now, it is a capacitor, so those voltage readings staying there means that there is real power on this thing, which is kind of cool, hey? But we obviously need to improve that a bit. I mean, actual brushes on the slip rings would do really well for that. But a rotating version does in fact work. So if you took this and put it into a stream, obviously the stream would be the thing that rotates it, and so Luke would be a stream, so to speak. Anyway, I hope you enjoyed this development of it. I certainly found it interesting that we'd be able to make a water wheel where the water wheel would directly generate energy, as opposed to us having to strap a generator onto it. And that does raise questions about the torque and whether we need torque in a water wheel to generate anything of that significance using this capacitive behaviour of the conductive ink. Anyway, I hope you enjoyed the video, I hope you enjoyed the series so far. Thank you very much for watching, and if you are experimenting with this, then please do share, because it would be fantastic for us all to be able to improve this together. Anyway, thank you very much for watching.